A machine such as this is often used in the laboratory to generate electricity. The generator is operated by a hand crank. At the electrodes, a spark is observed from time to time, indicating the presence of electric interactions and the flow of electricity. Even when the cranking is stopped, electric interactions persist. A spark forms upon closing the gap with a conductor. Let's remove these electrodes and replace them with long brass rods, from which we'll hang lightweight spheres covered with electrically conducting foil. The generator is started. The spheres move together, indicating electric forces are acting between them. A battery also generates electricity. We can connect it to electrodes immersed in chemical solutions. Again, motion occurs. Here in time-lapse photography, we can see the movement of the colored substances within the tube, indicating electric interactions. What is the relationship between the electric interactions that move the chemicals and the electric interactions that move the spheres? Let's try some experiments with the spheres, but first we'll narrow the gap between the electrodes. The spark is hard to see, but the electric interactions disappear. Now we'll turn the right electrode to minimize its interaction with the left one, and hang both spheres from the same electrode. This time, when the generator is operating, the spheres repel one another. However, when the gap is closed, sparking occurs and the repulsion disappears. What happens if the spheres are suspended from the other electrode? We turn it to minimize possible interaction between the electrodes. When the generator is started, the spheres again move apart. Thus, if the spheres are suspended from the same electrode, regardless of which electrode it is, the spheres repel one another. When the spheres are suspended on opposite electrodes, the spheres attract one another. Let's try to explain these attractions and repulsions using the electron and proton model of matter. Electrons, represented here by a minus sign, and protons, represented here by a plus sign, are present in all matter. We represent the many billions of electrons and protons contained in one of our spheres with these few symbols. If we add more electrons, the sphere is said to become negatively charged. It holds more electrons than protons. If we remove electrons, it can become positively charged. Now there are more protons present than electrons. An object which contains an equal number of electrons and protons has no net charge. It is uncharged. We can start with two uncharged objects suspended from a single electrode and use a generator to remove electrons from both of them. We observe experimentally that repulsion occurs. The two electrically positive objects exert a repulsive force on one another and remain apart. In the same way, if we start with two uncharged objects and use a generator to supply electrons to both of them, they again repel. These negatively charged spheres exert a repulsive force on one another, and again the spheres stay apart. When spheres are suspended from opposite electrodes, the generator can remove electrons from one sphere and add them to the other. Attraction occurs. The left sphere now has a positive charge and the right a negative charge. The attractive force between the unlike charges caused the spheres to move together. How can this force be measured? Here is an apparatus which will allow us to measure the force acting on a charged object. A metallically coated sphere is suspended by a non-conducting nylon thread from a sensitive balance. Turning the left knob releases the balance and illuminates the fractional gram scale. The balance shows that the weight of the sphere due to the force of gravity is 11 grams, indicated at the left, plus 0.130 grams, indicated on the fractional scale. The total weight is 11.130 grams. We'll record this reading in our notebook. A second sphere is supported by this non-conducting plastic rod. We have modified the generator by adding longer electrodes so that we are able to charge the spheres by touching them with the electrodes. As electricity is generated, each sphere is given a charge, one negative, the other positive. These two spheres should act like the spheres previously suspended from the two generator electrodes. That is, opposite charges should attract. The reading on the left, remember, is 11 grams. The fractional scale now reads 0.493 grams. The total weight, therefore, is 11.493 grams, which is more than the reading of the single uncharged sphere. What does this increase represent? The force of gravity causes the original weight reading on the balance. Now, with oppositely charged spheres, the balance reading increases by an amount due to the electric force. If we subtract the weight due to gravity from the total apparent weight, a measure of the electric force remains. Now watch what happens when we move the lower sphere up and down. The balance reading oscillates. When the lower sphere is brought closer, the apparent weight increases and then diminishes as we move the lower sphere away. Force and distance are interrelated. Let's measure these forces at various distances. Each of these blocks is 5 centimeters thick. By removing them one at a time, we can change the distance between the spheres. Initially, we'll adjust the spheres until their centers are 10 centimeters apart. Now we'll make sure the spheres are fully charged. The balance now reads 0.671 grams on the fractional scale, or a total of 11.671 grams, which is higher than the readings for the uncharged spheres. We'll record the reading for each distance between the spheres. At 10 centimeters, 11.671 grams. Now, by removing one block, we'll increase the distance between the spheres to 15 centimeters. The reading decreases with the spheres farther apart to 11.364 grams. Increasing the separation to 20 centimeters gives a balance reading of 11.263 grams. Finally, Let's separate the spheres by 30 centimeters. The balance reads 11.187 grams. Let's remove the lower sphere completely so that there is no interaction between the two spheres. With the distance large, the reading was 11.128 grams. This is the same weight within experimental error as when we started with an uncharged sphere. Now the electric force corresponding to each distance can be calculated. Subtracting the reading due to gravity from the reading at 10 centimeters gives us 0.541 grams for the electric force. In a similar manner, the electric force for each of the other distances is calculated. At a very large distance, the electric force is so small that, for our purposes, we can consider there is none. When these values for the electric force at each distance are plotted, they give a smooth curve. Data for other distances will give additional points lying on the curve. As the distance of separation between charges increases, the force decreases. The equation for a curve of this type is F times R squared equals K, a constant. F is the electric force. R is the distance between the centers of the spheres. F times R squared should give a constant product. Let's find out. For the first measurement, 0.541 grams times 10 squared is about 54. In a similar manner, we can calculate the values for the other distances. The results show that the product of force times distance squared is constant within experimental error. This relationship, F times R squared equals K, applies to the interaction of oppositely charged spheres. It also is found to apply to the interaction of like charges. Thus far, we have seen that uncharged, that is, electrically neutral objects exert no force. Opposite charges attract, and like charges repel. The force of interaction between two charged objects varies with the distance between them. Let's apply these ideas to chemical behavior. Many solutions such as these contain charged particles called ions. In this cupric sulfate solution, the blue color is due to many billions of positively charged copper ions. Let's see what happens when we place these ions in a glass tube between two electrodes, which can be charged by a battery. The solution is poured in the space between two plugs of white gelatin-like material. The gel separates the solution from each electrode. The gel can conduct an electric current, but will not allow liquid to flow through it easily. The positive electrode will be on this end. The negative electrode will be on this end. The battery will supply electrons to the negative electrode and remove them from the positive electrode. When the battery is connected, the electric interactions can begin. We will compress 2 hours of actual time into 15 seconds using time-lapse photography. The blue color does move to the right, but not to the left. The positive copper ions move toward the negatively charged electrode and away from the positively charged electrode because of the electric interactions. Let's repeat the experiment with potassium chromate. Since all aqueous chromate solutions are yellow, we believe the yellow color is due to chromate ions. We'll pour the solution into the center section of another tube, arranged as in the previous experiment. This time, repeating the time-lapse photography, we again see motion. But the yellow color moves toward the left, toward the positive electrode, and away from the negative electrode. The yellow chromate ions must be negatively charged. Now, the apparatus has been modified so that the solution containing positively charged copper ions can surround the positive electrode. The solution containing negatively charged chromate ions is placed around the negative electrode. The battery charges the electrodes, and as you would expect, the colored ions move through the gel in opposite directions, consistent with their opposite charges. But here's a new effect. A brown region develops. Let's disconnect the battery. The central brownish region suggests that a new chemical substance has been formed where the copper and the chromate ions meet. What could such a new substance be? If we simply mix the original solutions, will this same brown substance form? Yes. Apparently, the gel and the electric current are not required. But copper ions and chromate ions are necessary. To understand this, let's keep in mind our previous equation, F R squared equals K. Remember that the positive copper ions and negative chromate ions not only move in opposite directions between the electrodes, but as the distance r between these ions decreases to atomic dimensions, the force F between the ions themselves must become large. Instead of passing one another, most of these oppositely charged ions attract one another, adhere, and form copper chromate, which has no net charge. It precipitates. Electric forces hold the solid together. The interactions of these solutions with electrically charged electrodes and with one another may be at least partially interpreted in terms of the presence of positively charged copper ions and negatively charged chromate ions. All electric interactions in chemistry may be interpreted in terms of two kinds of electric charges, which we call positive and negative. This knowledge of electric interactions helps us to explain the movement of ions and the formation of precipitates, and indeed the formation of all chemical compounds.